Hello, welcome to WICKERSON Studios. I am continuing with this Geometry to the Point and Beyond video series, and we're ending the point section before we go into lines. And I'm going to do that through ending with a little bit of the math library and putting that to use. And what I'm going to do is follow up initially with these basics and geometry points on my GitHub for the patrons. And actually, this series has done pretty well. It's gathered a few more patrons, and I think it's actually pretty good. Now, from these videos, you can basically generate and play with all this. But if you are interested in this script, the master to the point 001, then just have a look at that and see if those are the files that you actually are interested in getting. And then down below, I'll also have this kind of sidebar of examples of what I played with and generated through this whole series. So I will continue. Let's turn off the turntable. Let's take this over to shaded. Let's ditch this geometry here. Put that to disable, and let's jump right in here with where we want to go in the XY plane. Let me eat my pretzel, and we'll get started on scripting in Python using the math library. So the first thing we're going to want to do, we'll leave our import Rhino. Import Rhino script syntax as RS, which will be fine. But if we are going to use the math, we're going to want to import. You could just import math, but I'm going to actually import math as M, which saves typing. But whenever I type M dot, so I'm going to try not to use that as a variable, you'll see where I can access properties and functions and methods of the math library, which should be good. Let's create a points array or a point list, whatever you want to call it. I guess since we're in Python, we should call it a point list, an empty list. And let's do an iteration for I in Rhino script. Now, this is very interesting because you'll have a heck of a lot of trouble trying to get decimals for dealing in trigonometry within Rhino Common Python Ghpython node. It's much easier to deal with doubles, decimals, floats in C#. But for this one, you're going to have to go into the Rhino script function fRange, which allows a float range to take place. And converting this over to range within Rhino Common, I've had a nightmare with it. I've had to import NumPy, or I don't know. I had to do a bunch of different scripting that it was just getting to be such a challenge. There's a bunch of articles on Grasshopper and Food for Rhino, the Rhino forum pages. But let's jump in here and let's have a float that will start as a float. Actually, let's call it that, float. Float. Well, it's start. What should I call it? Let's call it start float f. And I'll just leave it as a small f because that'll kind of remain. And actually, what we should do is just have fun with this and call it f start because we have an f range. Let's have an f stop, which is kind of nice. Sounds like a camera, like we're developing film. And let's have a step in the decimals that's very small. So we're going to have a let's have a just f step. But keep in mind that we want to keep that small for the trigonometry. Colon will be like 4i in f range, Rhino script f range, it's start, stop, step. Then, that's what I always think the colon stands for. It's a good way to think about that. We're going to set x equal to the iteration I value multiplied by whatever we want within the math nodes. So this is going to get a little exciting. I'm going to start simple with this and just type in sign and keep the sign of I. So it's going to be a pretty simple helix to start with. And y, we're going to set that equal to the iteration I times m dot. So we're not putting a variable m in. That's math library. Cos, which should give us the helix form. And we can go iterate that through the I iteration. And z, we're going to throw in as equal to I. So that's pretty boring. But that'll do the trick. All you have to do now is staying within your, I don't know if I want to stay within the loop to do this, but let's do it. Let's point equal to Rhino script, add point, and do the autocomplete. And let's just get the script up and running at XYZ. And then let's append the points as our point list, append that with those points. And at this point, I'm going to actually with the point, not the points. And then I'm going to leave the scope of that function. I'm going to output my points out equal to points. Now that's a simple script coming from this Chinese text. It's enough to start with and get you going. Now, what would you do with it? Well, first of all, you're going to want to run in here, and you have your values x, y, z. Since they're being organized here, you're not going to need them here. You're actually going to want to change these to F start, and definitely with the F, float is not a double in Python, so just F, set it to float. F stop, set that over to the float. I think I missed it. Kids are making animal noises, but that's what happens. And F step. And I'm going to set that to a float. Now, I am going to set my float because I want a very low number. So I'm going to set that to 1.00 and keep my F step very small. Now, the F stop itself, I guess I can climb in value to that. What would be some good numbers for that? Thinking of a stop value. Oh, we could take it right up. We could just use the integers, but leave it as a float. 12.00, which allows to climb to like 100 or whatever we want to do. And because we're dealing in decimals, it doesn't have to be an integer value there. And our start value can start at 0, but let's do a simple 2.00 so we can start somewhere off the base. And we'll start at 0 just to see if the script's running. And our outputs, obviously, get into your node, type in your values, points underscore out, and that should do it. Let's run it and see if we have any luck. We have a problem. And the problem is F start, F stop, F step. Let's take a look at where that is. Must be less than 0. Step must be less than 0. Oh, that makes sense. I was supposed to. So obviously it can't run at 1 step. So that's very interesting. I'm going to pull that down there and just pull back that. Just pull that back just a little bit to 99. See if that makes a difference. I wouldn't have thought I'd have to do that, but let's try it again. That is less. No, it said it has to be less than 0. Doesn't make sense to me if I look off the script, because 0.1 and I would think that step value could be a decimal like that. I have to wonder why it's challenging me to do that. And so let's take a look a little deeper in here and see what's going wrong. F range, Iron Python, FX range. Maybe I should get an FX range going as a function, see if that makes a difference. Nope. I have to take a little break. Step must be less than 0. Let me take a break and I'll see what I've got going on wrong. A little bit of a delay, 5 seconds on my sound. Now I'm going to show you why the F range just causes me such trouble. And if somebody can explain this to me, I'd really appreciate it. What you can see is that the F stop, hard-coded in here, doesn't work at 100.0. It just doesn't work. But if you set it as a stop at 100.0, it'll work fine. So you really don't even need this. But then it's not parametric. You can't change the end of it, which is frustrating. And it has to be something to dealing with the decimal as it turns what used to be integers in a range tool over to floats. So the f-stop doesn't matter. It's like, it can be any range. And you can produce some really wonderful geometries. And you actually get these really wonderful patterns of lines. And that's really where I wanted to go with this as we move through these geometries to produce these lines. But I still have yet to figure out why I can't take that hard-coded 100.0 and make it work. Because every time I type that in there as something like, you'd think it would just read it as a double, but or as a float, but it just causes trouble. It might be the maths. It might be the f range function itself. I know there's an fx range function. I still have yet to figure out how to deal with Rhino common and the geometry and dealing with range within that, maybe just as a range function with decimals. But obviously I've had to rein this back in, pull back in that f-stop, pull out the f-stop and just have it hard-coded in at 100.1. So until I figure that out, it's been something I've been playing with for the few months, but it's a little frustrating. But it is nice to get these geometries. So once we've started on that, I want to show you where you can kind of go with this. I am going to take that data, and definitely I'm going to do what it looks like it wants to do, which is go into a curve as an interpolated curve, and then you can see exactly what we have. Now, what's very nice about that, I'm just going to deviate a little bit here, going back in, because we're dealing with some pretty interesting data. Let's take a look at this, what the points look like. Well, they're one branch of 64 items. And I really don't know if I want it to be one branch of 64 items. I wish I could blow that up and have it count in another direction. So if I took a flip matrix tool that some people are used to using, which can really make a mess of your data and change up what's going on. Let's go to sequence. I think it's over here. Flip matrix. And let's see what we're pulling out if we flip that matrix. We've now got 161 branches with one item on each, which is making for a totally different geometry. If I start to do this, it's not going to do anything. What I'd like to be able to do is take that data that was in here and start breaking that up and partition the list and do things like that within here. So you may want to, I don't know, we'll go through here, not shift bash math trees, prune trees. Let's go in the list, see what we have. Let's partition list and see what kind of chaos we can do to this. Like, what if we partition that list and thought about that as a series of points coming out and just had a number slider like 12 and said, let's partition it every 12 and get these chunks. And now you have pretty interesting data that if we start to interpolate that, you'll see you get this kind of split patterns of curves, which are kind of interesting as they start and stop. And at this point, you might want to, with that list, this chunky data, I guess you can think of it as chunky data, go in here and try this flip matrix tool and have a little fun with this. And this is really playing with data trees and what you can do. And now we've got a very nice pattern that kind of starts and stops and behaves pretty decently. So when I start taking this function down, you can see I can end up having these really nice forms as they whip around. And of course, if I took that and put it directly into here, it would look like that. If I took the chunks and put it directly in, it would look like that. But if I do the flip matrix, I'm starting to get some of the geometries I wish I could get from this tool. And at that point, that woven and stitched together and starting to play with that, let's do something pretty simple and fast-paced with a little bit of a pipe. And you can see what we can do with, let's take it up to 2.00 and see what we can do without capping, because that'll slow it down also. There we go. We've got a pretty nice pattern that's based on sine and cosine, and there you go. I like it. I'm counting these things. I'm looking at them and saying, how many do I actually have there? This pattern is making for a very interesting thing that happens. Like, take a look at that partition list and the chaos and the weaving and the stitching and what actually happens. So that's where you can go from a very simple script. And like I said, I didn't 100% solve it for myself. We'll call this a to the point underscore math library. And already we've made a pretty interesting geometry from something very simple. I do like that little pattern, even though most of it happens after by dealing with the partition list. And that's why when you get these basic scripts, you really should go in, write something. Because what happens when I go in here and I do something totally different? So let's take this data here. Let's take this whole monster and say, okay, that's a pretty cool form. And let's bring that down here and have a little more play with it. So we've got that initial one that's there. And we'll take that one off. Actually, I really like that shape. Let's disable that. Let's go into here, close that script to that one. Let's open this one up and say, well, there was lots of choices in here as I thought about those geometries and made that the geometry I'm looking at. So what happens when I work computationally? Not parametrically within the Grasshopper node script system, which is computational, not through CAD over here in the Rhino window. I'm building this nest. But let's go into here and see with the coast, keeping the sign the same. Actually, let's totally change it up. Well, I always say I'm going to do something, then I don't. Like, what I like to do is just, like, have fun with this and, like, times I. And that's going to blow it out of the water, I'm pretty sure. There we go. Yeah, it exactly blew it out of the water. But you get incredible patterns because you're just playing with the maths within there. And this, once again, is where I was very excited with processing with the coding train with Daniel Schiffman, how he really worked within processing to make changes. So I'm going to go down here and with this one, go back to the math library dot and say which other of these ones really would work. And if I find 5 or 6 that'll work, I'll run an enumeration conditional script in here and make some really magic things happen. So let's just keep it on and let's go down and see what I like to use. I really like to use log1. I think I can. I don't know. Log1p, let's test it. Yeah, look at that. I mean, like, that is the magic of this. Never would I ever script this object, and you see how it's kind of off to the side. And when you start to play Geometrica with this, this is the power of the 4 view parts in Rhino, that you can actually go in, have a lot of fun, size it all to what you're looking at. Look at that slight bend that's on there. You don't even notice it, but it's there because of logarithm. And you've got a beautiful pattern. You can play with this in all different shapes. Got a great shape here for rendering. And at this point, I would start, then I would start having fun, and I have honestly no idea what's going to happen geometrically when I do that. Well, I could have guessed. I should have guessed, actually. I'm a fool. You start bringing in things. So if I did that one, there's a pretty nice pattern that works. So I might want to have a conditional, if enum, so you make a variable enum is equal to, and I do this a lot because it's kind of like a Boolean. I like it. If that's that, then I will set y to this. Else, else, and I don't know if this is going to work. If I should be in this order, I should be tucking it between these variables. I probably shouldn't be. Else, we're going to just script y is equal to I, and I haven't figured out whichever one I want, so it's probably good to play it safe with cos, and go back to your I, because you know that one works. And then see if it keeps running the script afterwards, or if it leaves or jumps out of this for loop. If it does, I'll have to tuck this stuff back upside. Let's do that. And of course, enum is not put in here yet, so I have to go back into here, and then I can just set a Boolean toggle on here, because that's the same as having 1 and 0 enumerated. So we're going to do enum, and I'm starting to use enum a lot lately because I really find it handy. You could have a Boolean and just do the type hint Boolean, but I don't mind. It's this picture that screws this up whenever I do this. Type hint. Oh, it's such a pain. Type hint, maybe because let's do an integer, and let's just set that to Boolean toggle. You can set it to 1 and 0. But Boolean toggle makes sense. So that's set to 0 now. Let's run it as a test. And something went wrong as enum at false. Yeah, it's jumped out of my loop and it won't solve it, because that's not where you want to be putting that. What I'll probably have to do is grab this data, pull that out, and say I'll probably have, I hate copy and paste text too often, but I think this would actually work a little better. Let's tab this one over. Let's copy that one there. And yeah, this is what it's all about. You get in here and you play. So if you don't delete things, you play. Let's go in here and have a little fun. Put that in there. Do a test. And there, it might have been working. Maybe I was fine to do it before. So there it is true, and there it is false. So I've got a nice enumerated script that does a couple of different geometries. I can pull it into those final little patterns there, and I really kind of like that. I mean, now why do I need it on that angle? I don't, but that's just the nature of using those different maths. I do like it. It's fairly parametric moving through here, and you get some nice patterns in the 2D pattern. You can relate this geometry. So start to think of like product design. Think, I need this as a coaster. I need this as the top of a spoon. I think I just went to 0 and it's going to botch it. But look at that pattern. Like, I would never normally make that, but math, I totally think is beautiful. Let's set it back on the other one. So what happens if that object becomes your cup bowl system that situates on something that's other mathematically related? And that's where I am totally passionate about this, and I'm in love with what I accidentally discovered. Boy, I hate this jumping because of this screensaver. It's my ugly face that ruins everything. Let's go back into here and just go into artistic. And there we go. We've got a nice object that's got a few problems down here for fabrication, because that's just a tendency, and you may have to Boolean union or crop that out. But honestly, it's infinite. It's revealing. It's what it's all about. You work computationally. You play within here. If you like what you've done, save it. You've got it set up as another experiment. Save it as another doc. And that's why, as I teach the basics, which so often I can't find online, I find the basic programs to learn C# and Python, and that's the way people learn. But I'm nearly 50 years old, and I don't want to learn that way. I want to play. I really want to get in here and look optically at what I've actually ended up making. And I'm starting to honestly think of this as the end of a utensil for grabbing at a certain scale, rounded on this side. And I'm one to cast metals. And when I'm done casting metals, I still have cutting, cleaning, chasing, finishing, patining, working. I don't mind using Grasshopper and computational studies to get me to a certain level of fabrication, and then I take over from there. So very excited about this discovered form that's there. I'm rambling on a little bit, but it's been a long day. First day back at school, trying to get students to really in sculpture explore this as an item to make discoveries, just like paint, just like fabric, just like textiles, just like topography, just like printmaking. You got to get in there like Jean Dubuffet, Art Povera, Brute Art, Dada, and find out what's within this and what's worth studying. So very passionate right now. I'm very excited. I'm going to put these first scripts up, which would have been very dull, and nobody would have joined my Patreon to see these basic scripts they can get online for free. But they may want to join my Patreon to get used to this and to really have a sense of, why not make it all playful? Why not jump in here? This is going to take a while. There you go. Why not make something so clustered and fun and playful like that? Just to have fun in your own craft and see what you actually want to generate. And thanks again for watching. WICKERSON Studios.